Welcome to problem 3. I got very excited when I read this because while studying, I worked a little on this function. Here you can see what I've been working on. The Galois group of points of order 3 on one elliptic curve. That was actually, I didn't solve it completely, but I worked enough on it to know that I would be able to do it. And then the denominator of NP, which is what this problem is about. I also wanted to work on the group of point modulus Q equals 7, so over the finite group. What was that exactly? Yeah, that was in F7. And then the same with F9, the points of F9. And you see, previously I haven't been able to, I've been rather alienated to these fields of prime power. But after reading the book on fields and fields extensions, it was easy to me. It was just an algebraic extension of the number fields that I know so well. So I actually was able to, and I found out how to make Mabel do the algebra. So that was very nice, and I can do that. But this, I defined the general curve, the sum of 2 points, and the double of a point, and tested then they worked. And then we took an arbitrary point P and found the double of it. So in the denominator we have f of x itself, and P3, then I added P2 and P, and there we got this guy in the denominator, and it's squared, which you already know. And then P4, then I doubled P2, and that is actually difficult to find here. We've got it. So we've got the points of order 2 here, and then here we have, that must be F4 squared, having the right degree 6. So when I saw this problem, I thought, wow, this may give us a recursion formula for fn plus 1, and then we'll be able to find all these expressions recursively. But I don't really know if we will be able to. Now, my first idea was to use the addition formula, Pn minus 1 plus y stars P of z, and then use recursion. I don't think that's a good idea, because then we have to know the numerator of the expression. So another idea is to look at the function and then see where are the poles and where are the zeros. And now the poles are exactly the poles of the zeros of Fn. But, and they come to order 2. So that means that instead of, maybe we should consider the function this guy has no poles because they've been eradicated by this. So we just need to check the zeros of this function. And that's the solutions to that means that the 2 points have the same x value. So could the y value be the same? So can these two be the same? Mm-hmm. You can see what I think, the way I think we might solve it is that if they are opposite, the two y values, second coordinates are opposite, then the sum of these 2 points is infinity, because the x values are the same. I had a thought before, now I lost it. The point, what I was going on is that the set itself either is of order n minus 1 or order n plus 1. But I've just lost it. And of course, we still have the problem whether they might be the same. Oh, there are 2 possibilities. So they may be the same point or they may be opposite points. In that case, that means that P has order n minus 1. they may be opposite points. Mirrored in the x-axis. And then P has order n plus 1. And of course, all the points of order n minus 1 will occur like this, and all of order n plus 1 will occur like this. So I believe that this is the list of all the zeros. So I believe this gives n minus 1 times fn plus 1 of z. Wow. I believe that was it. So it just occurred to me that I missed the constant here. So what I argued on the first page was that we must put a constant on here because they have the same poles and zeros. So within one lattice. So to find the constant, we need to look at the poles at z equals 0. So, and I needed more paper to be able to do it. So, poles at z equals 0. First, this is 1 divided by n squared z squared. 1 divided by z squared equals 1 minus n squared divided by n squared polar of order 2. And this, I made a mistake. This should be x, where x equals the Weierstrass P of z. So the order in the numerator is 2n. What is the order of fn really? I missed that. I'll just have to look that up, how many points we do have. So it's n squared minus 1/2. So we'll just look at the order. In x. Plus, minus, it was n squared minus 1, n plus 1, n squared minus 1/2. I think I'm wrong here. That's something I should have known. It says the leading term at z equals 0 equals n divided by So we can just write up the leading term at z equals naught. Leading, how do you spell that? L-E-A? Yeah, L-E-A. So, what did it say it was? It depends upon whether it's... that's F tilde. So we should have it from F as well. Oh, now I realize I'm reading this page. And I'm realizing that it was Fn squared that they were looking at. So so they do come with a factor n, and then the order of z So I believe in general it is n divided by z to n squared I should have prepared this. This is silly to spend your time doing this. And then minus 1. That's what it directly says in case 1, where n is odd. Where n is even, it's f tilde, and then they multiply by the 3 ones. So we see and even order. So they multiply by the derivative, which gives a factor 3, so that's the same. So this one should hold in general. So now let's do the leading term. Then we divide by this guy, which is n squared, z in 2n squared minus 1. No, minus 2. We must double them both. So we get n squared minus 1 divided by n squared. And then these two guys cancel, and this, they cancel. So we get z to minus second, or z in the second in the denominator. So that finishes it. The constant c must be minus 1, like stated in the problem. So that was it. I was so pleased with being able to find this that I didn't prepare at all. So now you see what happens when I don't prepare at all.